Now in this lecture we'll answer two questions. In the first question we find out the radius of this circle, and in the second question we'll find out the area of the circle using two different methods. Let's start with the first question. In the drawing we have a circle. This is the right triangle ABC. Side AB equals to 3 units in its length. This is line segment AED. This is also equals to 3 units in its length. This is the short line segment DC. This is equals to 1 unit in its length. Again, our task is to find out the radius of this circle. So here we can implement rule 25. A bit quickly on rule 25. Rule 25 is also called the tangent second theorem. According to rule 25, if from a common external point P, we will draw a tangent PA to a circle. Tangent PA tangent to this circle at point A, and a line segment PC is also defined as a secant, and line segment PC cuts the circle at 2 points B and C. So in this drawing the following equation is true, that PA square equals to PB times PC. Again, PA square equals to PB times PC. So we can actually implement rule 25 in our drawing. What goes in our drawing? If we focus on this common standpoint point C, from this common standpoint point C, we have tangent CE, that is tangent to this circle at point D, and we also have secant CA that cuts the circle at 2 points D and A. So all the requirements of rule 25 are satisfied, and therefore we can implement here rule 25. So moving on. So if you focus on the common standpoint point C, according to rule 25, the following equation will be true, that CE square equals to CD times DA. Equals to CD, again, CE square equals to CD times CA. And again, according to rule 25, the following equation is true, that CE square equals to CD times CA. Again, if we focus on the common standpoint point C, according to rule 25, the following equation will be true, that CE square equals to CD times CA. CE is the missing side, so limit is CT, so it is CE square equals to CD. CD equals to 1 times CA. CA in total equals to CD plus DA. This is 1 plus 3, this is 4. So CA in total equals to 4. So according to rule 25, CE square equals to 1 times 4. 1 times 4 is 4. So CE square equals to 4. Here we take a root out of this equation and finally get that CE equals to the square root of 4, that is 2. So tangent CE is equal to 2 units in its length. This is tangent CE that is equals to 2 units in its length. In the next step, we will implement the Pythagoras theorem on this right big triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I'll copy the right triangle ABC in a new page and we will implement on it the Pythagoras theorem. The hypotenuse AC equals to 1 plus 3, that is 4. AB equals to 3 units in its length, according to what is given as the equation, and BC is the missing side. Here by PT is the abbreviation for Pythagoras theorem. Actually, this is the right triangle ABC that is coming from the original domain. This right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So I write it down. AC squared, that is the square of the hypotenuse, is equal to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16, and it equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing side, so we leave it as it is. So in total, we found that 16 equals to 9 plus BC squared. Here we will subtract 9 from this equation, and we will get that 16 minus 9 is 7, so 7 equals to BC squared. Here we take a root out of this equation, and we get that BC equals to the square root of 7 units in its length. So actually, this is side BC that equals to the square root of 7 units in its length. What is the length of this missing line segment BE? From the drawing it is very easy to see that BE equals to BC minus AC. So I write it down. BE equals to BC minus AC. So BE equals to BC is square root of 7 minus AC equals to 2. So in total B equals to the square root of 7 minus 2 units in its length. This is line 7BE. This equals to the square root of 7 minus 2 units in its length. In the next step, we'll join points O and D together by a straight line. According to what is given in the question, point O is the center of the circle. So point O is the center of the circle. Point E is the point of the circle itself. Therefore, OE is the radius of this circle. We define the radius of this circle as R, so O equals to R. Is the radius of the circle. The radius OE is equals to R. The radius OE is drawn to point E, that is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we will do another construction, that is to say from point O, that is the center of this circle, we will do perpendicular on AB. Again, from point O, we will do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB, this point is point L. By doing this construction, we're going to do quadrilateral LOEB. Inside quadrilateral LOEB, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral LOEB we have 4 rectangles. Therefore, according to rule 5, quadrilateral LOEB is a rectangle. So, write it down. Quadrilateral LOEB is a rectangle according to rule 5. Because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LOEB, side BE is equal to the opposite side LO, but BE is square root of 7 minus 2, therefore the opposite side LO must be also equal to the square root of 7 minus 2 units in its length. So I write it down. LO equals to the square root of 7 minus 2 units in its length. Likewise, according to the same rule, in the same rectangle LOEB, side OE must be equal to the opposite side LB. But OE is R, therefore the opposite side LB must be also equal to R units in its length. What is the length of this missing line segment AL? From the drawing it is very easy to see that AL equals to AB minus LB. Again, AL equals to AB minus LB. So I write it down. AL equals to AB minus LB. So AL in total equals to AB. AB is 3 according to what is given in the question. Minus LB. LB is R. So in total, AL equals to 3 minus R units in its length. this is side AL, this is equals to 3 more units in its length. In the next step, we join points O and A together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of the circle, is equals to R according to our definition. In the next step, I'll copy the right green triangle ALO in the new page, and we will implement the Pythagoras theorem on this right green triangle ALO. Here by PT is the equation for Pythagoras theorem. So actually, this is the right green triangle ALO that goes from origin to origin. In this right triangle AO squared, that is the square of the hypotenuse, equals to AL squared plus LO squared. So it's down. AO squared, that is the square of the hypotenuse, is equal to AL squared plus LO squared. AO is R, therefore AO squared is R squared, and it is equal to AL squared. AL is 3 minus R, therefore AL squared is 3 minus R squared, plus LO squared. LO is square root of 7 over 2, therefore LO squared is square root of 7 minus 2 squared. So in total we found out that R squared equals to 3 minus R squared plus 7 minus 2 squared. So R squared equals to 3 minus R squared. 3 minus R squared equals to 3 squared, that is 9, plus R squared, minus 2 times 3 minus R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared is equal to 0.417. So in total we found out that R squared equals to 9 plus R squared minus 6R plus 0.417. Here we have R squared on both sides of this equation, so R squared will get cancelled. After we cancel R squared on this side of the equation, we left with nothing, that is to say 0. And on the other side of the equation we have 9 plus 0.417, that is 9.417 minus 6R. So in total we found out that 0 equals to 9.417 minus 6R. Here we will add 6R to this equation, and we get that 6R equals to 9.417. Here we will divide this equation by 6, and finally we get that R equals to 9.417 over 6 is 1.57 units. So we actually found out that the radius of this circle, that is the radius that we are looking for this question, is equal to 1.57 units in its length. So we finish with the first question. In the next step, I will present you the second question, and we solve the second question in two different methods. In the second question, our task is to find out the area of this circle. So in the drawing, we have a circle. This is 97 BC. This equals to 6 units in its length. This is called BA. This equals to 13 units in its length. This is 97 CD. This equals to 18 units in its length. Those two angles, they are both right angles. Again, our task is to find out the area of this circle. So, first of all, those two right angles are defined as one-sided interangles. The sum of those two right angles is, of course, equal to 180 degrees. And according to rule 27, if the sum of two one-sided interangles is equal to 180 degrees, then they must be located between parallel lines. The sum of those two one-sided interangles is equal to 180 degrees, and therefore they must be located between two parallel lines. That is to say, chord BA is parallel to line 7 CD according to rule 27. So I write it down. We should find out that chord BA is parallel to line 7 CD according to rule 27. In the next step, we define the center of this circle. This point is point O, and we do a construction, that is to say, from the center of this circle, that is actually point O, we do perpendicular on CD. Again, from the center of this circle, we do perpendicular on CD. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and CD. This point is point M. In the next step, we will extend the perpendicular OM by side line until it touches chord BA. And again, we will extend the perpendicular OM by side line until it touches chord BA. And we will define the touching point of the standard perpendicular OM with chord BA. This point is point N. OM is perpendicular to chord CD. We extend the perpendicular OM by side line until it touches chord BA. And because of the fact that according to rule 27, chord BA is parallel to chord CD, the extended perpendicular OM to chord BA must be also perpendicular to chord BA. Because of the fact that OM is perpendicular to CD, therefore the extended perpendicular OM must be also perpendicular to chord BA. Why? Because CD is parallel to BA. So this angle equals to 90 degrees, And this angle also equals to 90 degrees according to the rule that I mentioned. Those two line segments are parallel to each other, so the perpendicular to CD must be also perpendicular to BA, because they are parallel to each other. Okay, so by doing this construction, we created here quadrilateral BC and M. Inside quadrilateral BC and M, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-piece angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4-piece angle must be equal to 90 degrees in its size. So inside quadrilateral BCMN, we have 4 right angles, and therefore, according to rule 5, quadrilateral BCMN is a rectangle. Because it has 4 right angles. Here we can implement rule 19. Why? Because we have, from the center of this circle, we have perpendicular ON on chord BA. So, repeat quickly rule 19. According to rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. In the drawing, we have a circle. Point O is the center of the circle. From point O, we have perpendicular OM to chord AB. Again, from point O, that is the center of this circle, we have perpendicular OM on chord AB. And according to this rule, rule 19, perpendicular OM bisects chord AB. That is to say, it divides chord AB into 2 halves. The first half is AM, the second half is MB, and of course, the first half AM is equal to the second half MB. So AM equals to MB. So we can implement rule 19 in our drawing. Why? Because in our drawing, from the center of this second, that is to say from point O, we have perpendicular ON on chord BA. Therefore, according to rule 19, perpendicular ON bisects chord BA. That is to say, it divides chord BA into 2 halves. The first half is BN and the second half is NA. BA in total equals to 13. Therefore, each half must be equal to 13 over 2, that is 6.5. So the first half BN is 6.5. And the second half NA is also 6.5 units in its length, according to rule 19. We already found out that quadrilateral BCMN is a rectangle, but we know that the opposite sides of a rectangle are equal to each other. So in rectangle BNMC, side BN must be equal to the opposite side CM, but BN is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. ON is a perpendicular of this absolute straight line. So if we focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is a right angle according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do another construction, that is to say, from this point A, we will do perpendicular on CD. Again, from point A, we will do perpendicular on line 7 CD. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and line 7 CD. This point is point L. By doing this construction, we created the lower quadrilateral MNLA. Inside the lower quadrilateral MNLA, we have three right angles. The sum of three right angles is 270 degrees, so 270 degrees plus the size of this four pieces again, so that must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this four pieces again must be equal to 90 degrees in its size. So inside the quadrilateral NMLA, we have four right angles. Therefore, according to rule 5, quadrilateral MNLA is a rectangle. So write it down. Quadrilateral MNLA is a rectangle because it has four right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the lower rectangle NMLA, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this short line segment LD? From the drawing, it is very easy to see that LD equals to CD minus CL. Again, CD minus CL equals to LD. So write it down. CL equals to CD and LD. This is the short line segment LD. LD equals to CD minus CL. So LD equals to CD is 18 according to what is given to the question. CD equals to 18 minus CL. CL in total equals to 6.5 plus 6.5. That is 13. So CL equals to 13. So in total LD equals to 18 minus 13, that is 5. So if you found out that the short line segment LD is equal to 5 units in its length. This is the short line segment LD, this is equals to 5 units in its length. In the next step, we will extend line 7 DC by straight line until it touches the circle. And we will define the touching point of the extended line 7 DC with this circle. This point is point T. By doing this construction, we can do code TD. This is code TD. So here we can implement again rule 19. Why? Because we have perpendicular OM from the center of this circle, that is actually point O. We have perpendicular OM to code TD. This is perpendicular OM to code TD. And according to rule 19, the perpendicular towards any chords from the center of the circle bisect the chords. So according to rule 19, perpendicular OM bisect chord TD. If perpendicular OM bisect chord TD, it means that TM equals to MD. So TM equals to MD according to rule 19. So write it down. If you found out that TM equals to MD according to rule 19. Again, Tm equals to md according to rule 19. But md in total equals to 6.5 plus 5. Again, md in total equals to 6.5 plus 5. That is 11.5. So I can write down that md equals to 11.5 units in its length. And from this equation, Tm equals to md equals to 11.5. We derive that Tm is also equals to 11.5 units in its length. This is 97 Tm. This equals to 11.5 units in its length. So, from one side, Tm equals to 11.5 units in its length. But from the other side, Tm also equals to Tc plus Cm. Again, Tm equals to Tc plus Cm. So, write it down. On the other side, Tm equals to Tc plus Cm. So, Tm equals to 11.5 on one side, and from the other side, Tm equals to Tc. Tc is the missing side, so leave it as it is, plus Cm. Cm is equal to 6.5. So we solve Cm by 6.5. And from this equation, 11.5 equals to Tc plus 11.5 equals to Tm equals to Tc plus 6.5. We derive that 11.5 equals to Tc plus 6.5. Here we subtract 6.5 from this equation, and we get that the missing 97 Tc is equal to 11.5 minus 6.5 is 5. So actually, this is the short line 7 Tc. This is equals to 5 units in its length. In the next step, we will extend line 7 BC by straight line until it touches the circle. And we define the touching point of the extended line. We define the touching point of the extended line 7 BC with this circle. This point is point Q. By doing this construction, we can derive code BQ. This is code BQ that intersects with code TD at point C. Again, code BQ intersects with code TD at point C. And again, code BQ intersects with code TD at point C. The intersection point occurs at point C. So, write it down. Code PQ intersects with code TD at point C. At point C. So here we can implement rule 15. Repeat quickly rule 15. According to rule 15, if code AB intersects with code CD at point O, then the following equation is true that AO times OB equals to CO times OD. So in the drawing we have a circle. This is called AB. This is a circle called CD at point O. So in this drawing the following equation is true that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 15 in our drawing. Why? Because in our drawing we have called BQ that intersects with called TD at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. According to rule 15, the following equation is true that TC times CD equals to BC times CQ. Then again, according to rule 15, TC times CD equals to BC times CQ. So I write it down. TC times CD equals to BC times CQ. And again, according to rule 15, the following equation is true. The TC times CD equals to BC times CQ. TC is 5 times CD. CD is 18. And it is equals to BC. BC is 6. Times CQ. CQ is the missing side, so we leave it as it is. So in total, if we found out that five times 18 equals to 6 times CQ. Here we will divide this equation by 6. And we get that CQ, the missing line segment CQ, is equal to 18 over 6 is 3, and 3 times 5 is 15. So CQ equals to 15 units in its line. This is the missing line segment CQ that is equals to 15 units in its line. In the next step, we'll join points Q and A together by a straight line. Join points Q and A together by a straight line. So we join points Q and A together by a straight line. By doing this construction, we created here peripheral angle QBA. This is peripheral angle QBA. That is equals to 90 degrees in its size according to what is given in the question. And peripheral angle QBA subset on code QA. Again, peripheral angle QBA subset on code QA. So here we can implement rule 5. I'll click on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in size must subset on the diameter of the circle. Hit again. Any peripheral angle that is equal to 90 degrees in size must subset on the diameter of the circle. So in the drawing we have a circle. This is peripheral angle MAN, that is equal to 90 degrees in size, and therefore peripheral angle MAN must subset on the diameter of the circle. And indeed, peripheral angle MAN subset on MN, that is the diameter of this circle. So, according to rule 5, any peripheral angle that is equal to 90 degrees in size must subset on the diameter of the circle. We can definitely implement rule 5 in our drawing. Why? Because in our drawing, we have peripheral angle QBA. This is peripheral angle QBA. is equals to 90 degrees inside, and therefore, according to rule 5, angle QBA must subtend on the diameter of the circle. Angle QBA subtend on chord QA, and therefore chord QA must be the diameter of the circle according to rule 5. So I write it down. If you found out that chord QA is the diameter of the circle according to rule 5. We know that the diameter of any circle is twice as long as the radius. So if you define the radius of this circle as r, then the diameter must be equal to 2r. So QA equals to 2r. This is called QA. It is also the diameter of the circle that equals to 2r. In the next step, I'll copy the right triangle QBA in a new page, and we will implement on this right triangle QBA the Pythagoras theorem. Side BQ equals to 6 plus 15, that is 21. Side BA equals to 13 units in its length according to what is given in the question, and the hypotenuse AB is equal to r, it is the radius of the circle also. So I copy the right triangle QBA in a new page, and we will implement on this right triangle QBA the Pythagoras theorem. The only missing variable is r, so by implementing the Pythagoras theorem this right triangle QBA, we find out the value of r, that is the radius of this circle. And the area is pi r square. This way we find also the area. We square the radius, we multiply it by pi, and then this way we find out the area of the circle. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle QBA that according to the original drawing, it is right triangle QBA according to the Pythagoras theorem. QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. So I write it down. QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. QA is 2r, therefore QA squared is 2r squared, that is 4r squared, and it is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441 plus BA squared. BA squared is 13, therefore BA squared is 13 squared, that is 169. So in total we should find out that 4r squared equals to 441 plus 169. So 4r squared equals to 441 plus 169 is 610. So 4r squared equals to 610. Here we divide this equation by 4 and find that r squared equals to 610 over 4 is 152.5. So if you found out that r squared equals to 152.5, our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. Therefore, the area of our circle must be equal to pi times r squared, but r is 152.5, so r squared is 152.5, so we substitute r squared in this expression by 152.5, and finally we get that the area of our circle is equal to 152.5 pi square units in its size. In terms of numbers, the value of this expression 152.5 pi is equal to 479.09 square units in its size. So according to the second method, we found out that the area of this circle is equal to either 152.5 pi square units in its size, so in terms of numbers, the area of this circle equals to 479.09 square units in its size. So we finished with the first method. In the next step, I'll present to you how to find out the area of this circle according to the second method. In the second method, we use the fact that we already found out that in the first method that this is 970 cubed is equals to 15 units in its length, and this is 970c is equals to 5 units in its length. So we use those two things that we already found out in the first method. So in the drawing we actually have chord TD that intercepts with chord BQ at 90 degrees at point C. Again, we have chord TD that intercepts with chord BQ at 90 degrees at point C. So here we can, whenever you have two chords that intersect with each other at 90 degrees, you can implement rule 26. So a bit quicker on rule 26. According to rule 26, first of all, rule 26 is true in any circle. So in any circle, if two chords, that is to say chord AB and chord CD, intersects with each other at 90 degrees, chord AB intersects with chord CD at 90 degrees, this again equals to 90 degrees. And their intersection point at this point O, that creates between them 90 degrees. So chord AB intersects with chord CD at 90 degrees. Then in this domain, the following equation will be true. The intersection point occurs at point O. So in this domain, the following equation will be true. That AO square plus OB square plus CO square plus OD square. Again, AO square plus OB square plus CO square plus OD square equals to 4R square. And R is the radius of this circle. And again, whenever you have two chords that intersect with each other at a right angle, you can implement rule 26. So here chord AB intersects with chord CD at 90 degrees at point O. Therefore, according to rule 26, AO square plus OB square plus CO square plus OD square equals to 4R square. And R is the radius of this circle. So you can implement rule 26 in our drawing. In our drawing, we have chord TD that intersects with chord BQ at point C at 90 degrees. So all the requirements of rule 26 are satisfied, and therefore we can implement in our drawing rule 26. So I write it down. We should find out that in our original drawing, chord TD, this is chord TD, intersects with chord BQ, this is called BQ, at 90 degrees, that is to say, at their intersection point, that is point C, the angles between them 90 degrees. This angle equals to 90 degrees. At 90 degrees, and the intersection point occurs at point C. This is point C. Repeat again. Found out that in our original moment we have chord TD that intersects with chord BQ at 90 degrees at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement in our drawing rule 26. According to rule 26, the following equation will be true: that TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared, and R is the radius of this circle. Repeat again. According to rule 26, the following equation is true: that TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. TC is 5, and therefore TC squared is 5 squared, that is 25, plus CD squared. CD is 18, therefore CD squared is 18 squared, that is 324, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36, plus CQ squared. CQ is 15, therefore CQ squared is 15 squared, that is 225. And it is equal to 4R squared. So we have found out that 25 plus 324 plus 36 plus 225 equals to 4R squared. $25 plus 225 is 250. So 250 plus 324 plus 36 is 360 equals to 4R squared. So 250 plus 360 equals to 4R squared. 4R squared equals to 250 plus 360 is 610. So in total we actually found out that 4R squared equals to 610. Here we divide this equation by 4 and finding that R squared equals to 610 over 4 is 152.5. So we found out that R squared equals to 152.5. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is R squared. So the area of our circle must be equal to pi times R squared. But R squared is 152.5. So we substitute R squared by 152.5 in this expression. And we get that the area of our circle is equal to either pi times 152.5 square units inside. So in terms of numbers, the value of this expression is equal to 479.5 0.09 square units in its size. So actually in both methods we found out that the area of this circle is equal to either 152.5 pi square units in its size, or in terms of numbers, the area of this circle is equal to 479.09 square units in its size. So we finish with the second method and the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our task was to find out the radius of this circle. So in the drawing we have a circle, and this is the right angle triangle ABC. This is angle ABC, this is the right angle. Side AB equals to 4 units in its length. Line segment AD also equals to 4 units in its length. This is the short line segment DC. This equals to 1 unit in its length. Again, our task is to find out the radius of this circle. So first of all, we implemented rule 25 in our drawing. It is also called second tangent theorem. If we focus on this common example point C, on this common example point C, we have tangent CE. It's the tangent to this circle at point E, and we also have secant CA that cuts the circle at 2 points D and A. So all the requirements of rule 25 are satisfied, and therefore we can implement rule 25 in our drawing. According to rule 25, the following equation is true: that CE square equals to CD times CA. Again, CE square equals to CD times CA. And again, if we focus on the common example point C, the following equation will be true according to rule 25, that CE square equals to CD times CA. CE is the missing side of limited cities, so CE square equals to CD. CD is 1 times CA. CA in total equals to 1 plus 3, that is 4. And again, CE square equals to CD, that is 1, times CA, that is 4. So in total, CE square equals to 1 times 4, that is 4. CE square equals to 4. Here we took out of this equation, and we found out that CE, the missing tangent CE, is equal to the square root of 4, that is 2, the square root of 4 is 2. So CE, tangent CE equals to 2 units in its length. In the next step, implemented the Pythagoras theorem on this right big triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The perpendicular AC is 3 plus 1, that is 4. AB is 3, and BC is the missing side. So here, this is right triangle ABC, that according to the original drawing, in this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16, and it is equal to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9 plus BC squared. So in total, we should find out that 16 equals to 9 plus BC squared. Here we subtracted 9 from this equation, and finally found out that BC squared equals to 16 minus 9 is 7. So BC squared equals to 7. Here we took a root out of this equation, and I found out that BC equals to the square root of 7 units in its length. Actually, this is the missing side BC, that is equal to the square root of 7 units in its length. What is the length of this missing line segment BE? From the drawing it is very easy to see that B equals to BC minus CC. Again, B equals to BC minus CC. And again, B equals to BC minus CC. So B equals to BC. BC is square root of 7 minus CE. CE is 2. So total B equals to the square root of 7 minus 2 units in its length. In the next step, we join points O and D together by straight line. Point O is the center of the circle, point is the point of the circle itself, therefore O is the radius of this circle. We define the radius of this circle as R, so O equals to R. The radius of E is equals to R, the radius of E is drawn to point E, that is the point of tendency of tangent BC with this circle. Whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did another construction, that is to say from point O, that is the center of this circle, we go perpendicular on AB. And from point O, we go perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB, this point is point N. So by doing this construction, we get the quadrilateral LOEB. Inside quadrilateral LOEB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral LOEB we have 4 right angles. Therefore, according to rule 5, quadrilateral LOEB is a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LOEB, side BE must be equal to the opposite side LO, but BE is square root of 7 minus 2, therefore the opposite side LO must be also equal to the square root of 7 minus 2 units in itself. Likewise, according to the same rule, in the same rectangle LOEB, side OE must be equal to the opposite side LB, but OE is R, therefore the opposite side LB must be also equal to R units in its length. What is the length of this missing line segment LA? AL equals to AB minus LB. Again, AN equals to AB minus LB, so AN equals to AB, that is 3. According to what is given us in the question, minus LB is R, so in total AN equals to 3 minus R. In the next step, we join points O and A together by a straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of the circle, that is equal to R according to our definition. In the next step, I call it the right green triangle ALO in the new page, and we implemented the button also on this right green triangle ALO. This is the right green triangle ALO, this is coming from the original drawing. This right triangle ALO, AO squared, this is the square of the hypotenuse, equals to AL squared plus LO squared. AO is R, therefore AO squared is R squared, and it is equals to AL squared. AL is 3 minus R, therefore AL squared is 3 minus R squared, plus LO squared. LO is square root of 7 minus 2, therefore LO squared is square root of 7 minus 2 squared. So in total we should find out that R squared equals to 3 minus R squared plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared. 3 minus R squared equals to 3 squared, that is 9, plus R squared minus 2 times 3 times R, that is minus 6R, and square root of 7 minus 2 squared in total equals to 0.417. So in total we should find out that R squared equals to 9 plus R squared minus 6R plus 0.417. Here we have R squared on both sides of this equation, so R squared will get cancelled, so the term cancelled R squared on this side of the equation will be left with nothing, that is to say 0. While on the other side of this equation we have 9 plus 0.17, that is 9.417 minus 6R. So in total we should find out that 0 equals to 9.417 minus 6R. Here we added 6R to this equation, and we found out that 6R equals to 9.417. Here we divided this equation by 6, and we found out that R equals to 9.417 over 6, that is 1.57 units in its length. So we should find out that the radius of this circle, that is the radius that we are looking for in this equation, is equal to 1.57 units in its length. Because again, the radius of this circle R equals to 1.57 units in its length. So if you finish with the first question, in the next step I presented to you the second question, and we solved the second question by using two different methods. In the second question, our task is to find out the radius of this circle. So in the drawing we have a circle. This is line 7 BC. This is equals to 6 units in its length. This is called VA. This is equals to 13 units in its length. This is called CD. This is equals to called CD equals to 18 units in its length. Those two angles are both right angles. Again, our task is to find out the radius of this circle. So first of all, those two angles are defined as one-sided interior angles. The sum of those two angles is 180 degrees. And according to Rule 27, if the sum of two one-sided interior angles is equal to 180 degrees, then they must be located between parallel lines. The sum of those two angles is 180 degrees, and therefore they must be located between parallel lines. They must be located between parallel lines. So, according to Rule 27, chord VA is parallel to line 7 CD. Can repeat again. According to Rule 27, chord VA is parallel to line 7 CD. In the next step, we define the center of this circle. This point is point O. And we did the construction, that is to say, from point O, we do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and CD. This point is point M. In the next step, we extended the perpendicular OM by straight line until it touches chord VA. And we define the touching point of the extended perpendicular OM with chord BA. This point is point N. So OM is perpendicular on chord CD. Therefore, the extended perpendicular OM must be also perpendicular on chord BA. Why? Because they are parallel to each other. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to what I've explained to you. Okay. So here in quadrilateral CB and M, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees. So 270 degrees plus the size of this 4 fixing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 fixing angle must be equal to 90 degrees in its size. So inside quadrilateral BCMN, we have 4 right angles, and therefore quadrilateral BCMN is a rectangle. ON is perpendicular, therefore ON is absolutely a straight line. So if you focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is the right angle according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So here we can implement Rule 19. According to Rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. Point O is the center of the circle, so the perpendicular OM to chord AB bisect chord AB. Again, the perpendicular OM to chord BA bisect chord BA. BA is 13, therefore each half must be equal to 13 over 2, that is 6.5. So the first half is BN, that is 6.5, the second half is NA, that is also 6.5, according to Rule 19. So we have already found out that quadrilateral BCMN is a rectangle. We know that the opposite sides of a rectangle are equal to each other. So in rectangle BCMN, side BN must be equal to the opposite side CN. But BN is 6.5, therefore the opposite side CN must be also equal to 6.5 units in its length. In the next step we did another construction, that is to say, from this point A, we do perpendicular on CD. Again, from point A, we do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CD. This point is point L. When we do this construction, we get the quadrilateral MNLA. Inside quadrilateral MNLA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 physical angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 physical angle must be equal to 90 degrees in its size. So inside quadrilateral MNLA we have 4 right angles, and therefore according to rule 5, quadrilateral MNLA is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MNLA, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this missing line segment LD? LD equals to CD minus CL. Again, LD equals to CD minus CL. LD equals to CD minus CL. So LD equals to CD, that is 18, according to what is given as the equation, minus CL. CL in total equals to 6.5 plus 6.5, that is 13. So in total LD equals to 18 minus 13, that is 5. This short line segment LD equals to 5 units in its length. In the next step, we extended line segment DC by straight line until it touches the circle. We define the touching point of the extended line segment CD with this circle. This point is point T. By doing this construction, we get chord TD. This is chord TD, so we can implement rule 19 on chord TD. Why? Because we have from the center of the circle, we have perpendicular OM on chord TD. Again, from the center of this circle to this point O, we have perpendicular OM on chord TD. And according to rule 19, perpendicular OM bisect chord TD. If OM bisect chord TD, it means that TM equals to MD. TM equals to MD according to rule 19. Repeat again. Now we found out that according to rule 19, TM equals to MD. But MD in total equals to 6.5 plus 5, that is 11.5. So we can write that MD equals to 11.5, and from this equation TM equals to MD equals to 11.5, we derive that TM is also equals to 11.5. This is line segment TM, this is equals to 11.5 units in its length. So from one side, TM equals to 11.5, from the other side, TM is also equals to TC plus CM. Again, TM equals to TC plus CM. TM equals to TC plus CM. So from the other side, TM equals to TC plus CM. TC is the missing side, so limited it is, plus CM. CM is 6.5. So we substitute CM by 6.5, and in total we found out that 11.5 equals to TM, and it is equals to TC plus 6.5. From this equation, we derive that 11.5 equals to TC plus 6.5. 11.5 equals to TC plus 6.5. Here we subtract the 6.5 from this equation, and we found out that TC equals to 11.5 from 6.5 is 5. So this is the short line segment TC, this equals to 5 units in its length. So In the next step, we extended line 7BC by straight line until it touches the circle. We define the touching point of the extended line 7BC with this circle. This point is point Q. By doing this construction, we created chord BQ. So chord BQ intersects with chord TD at point C. And again, chord BQ intersects with chord TD at point C. The intersection point occurs at point C. So here we can implement rule 15. Repeat again. Chord BQ intersects with chord TD at point C. So all the requirements of rule 15 are satisfied, and so according to rule 15, the following equation is true that TC times CD equals to BC times BQ. Again, TC times CD equals to BC times CQ. And again, according to rule 15, the following equation is true that TC times CD equals to BC times CQ. TC is 5 times CD, CD is 18, BC is 6, and CQ is the missing side. So in total, if you found out that TC is 5, CD is 18, BC is 6, and CQ is the missing side. So in total, if you found out that 5 times 18 equals to 6 times CQ. Here we divided the equation by 6 and finally found out that CQ equals to 18 over 6 is 3, and 3 times 5 is 15. So this is, let me see, 97 CQ, this equals to 15 units in its length. In the next step, we joined points Q and A together by straight line. So in the drawing we have peripheral QBA. Peripheral QBA is equal to 90 degrees in size according to what is given in question. And peripheral QBA subtend on chord QA. Again, peripheral QBA subtend on chord QA. So here we can implement rule 5. According to rule 5, any peripheral that is equal to 90 degrees in size, like peripheral QBA, that is equal to 90 degrees in size, must subtend on the diameter of the circle. Again, according to rule 5, any peripheral that is equal to 90 degrees in size must subtend on the diameter of the circle. So peripheral QBA is equal to 90 degrees in size, and therefore it must subtend on the diameter of the circle. Peripheral QBA subtend on chord QA, and therefore chord QA must be the diameter of the circle according to rule 5. So QA is the diameter. The diameter of any circle is twice as long as the radius. If we define the radius of this circle as r, then the diameter of QA must be equal to 2r. So here, I copied the right big triangle QBA in a new page and implemented the Pythagoras theorem on this right big triangle QBA. This is side BQ, this equals to 6 plus 15, that is 21. Side BA equals to 13 units in its strength according to what is given in the question, and the hypotenuse QA equals to 2r. So actually, this is the right triangle QBA, that I copied from the original drawing. This right triangle QBA, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. QA is 2r, therefore QA squared is 2r squared, that is 4r squared, and it is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441, plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total, we found out that 4r squared equals to 441 plus 169. 441 plus 169 is 610. So in total, we found out that 4r squared equals to 610. Here we divided this equation by 4 and found out that r squared equals to 152.5. And again, r squared equals to 152.5. Our task is to find out the radius of this circle. Actually, we know that our task is to find out the area of this circle. We know that the area of any circle is equal to pi times the radius of this circle. The area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared, so the area of our circle must be equal to pi r squared. But r squared is 152.5, so we substitute r squared this expression by 152.5, and finally found out that the area of our circle is equal to 152.5 times pi squared in size. So in terms of numbers, the area of our circle is equal to 479.09 square units in its size. We finish with the first method. In the next step, I presented you how to find out the area of this circle according to the second method. In the second method, we used the things that we already found out in the first method. In the first method, we already found out that TC equals to 5 units in itself and CQ equals to 15 units in itself. So, because of the fact that we have here code TD, that is a substitute code BQ at 90 degrees at point C, we can implement here rule 26. According to rule 26, if two chords intersect with each other at 90 degrees, then the following equation is true, that AO square plus OB square plus AO square plus OD square equals to 4R square. Again, chord AB intersects with chord CD at 90 degrees at point O. So whenever you have two chords that intersect with each other at a right angle at 90 degrees, the following equation is true, that AO square plus OB square plus AO square plus OD square equals to 4R square, and R is the radius of the circle. So we can implement rule 26 in our drawing. Why? Because in our drawing we have chord TD that intersects with chord BQ at 90 degrees at point C. Repeat again, in our drawing we have chord TD that intersects with chord BQ at 90 degrees at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement in rule 26. According to rule 26, the following equation is true, that TC square plus CD square plus BC square plus CQ square equals to 4R square. Repeat again, according to rule 26, the following equation is true, that TC square plus CD square plus BC square plus CQ square equals to 4R square. TC is 5, therefore TC square is 5 squared, that is 25. CD is 18, therefore CD squared is 18 squared, that is 324, plus BC square. BC is 6, therefore BC square is 6 squared, that is 36, plus CQ square. CQ is 15, therefore CQ square is 15 squared, that is 225, is equals to 4R squared. So in total, 425 plus 324 plus 36 plus 225 equals to 4R squared. 25 plus 225 is 250, and 324 plus 36 is 360. Equals to 4R squared. So 250 plus 360 equals to 4R squared. 250 plus 360 is 610. So 4R squared equals to 610. Here we divided this equation by 4, and we found out that R squared equals to 152.5. Our test is to find out the area of this circle. After we know that the area of any circle is equal to pi times the radius of this times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is R squared. So the area of our circle must be equal to pi R squared. But R squared is 152.5. So we substitute R squared, this expression, by 152.5. And finally found out that the area of our circle in both methods is equal to either 152.5 pi square units in size. So in terms of numbers, the area of this circle is equal to 479.09 square units in size. So in both methods, we arrive to the same result. Okay, thank you very much.